Okay, so you will begin with 8 milliliters of dichloromethane that will be mixed with 8 milliliters of cyclohexane and 8 milliliters of paraxylene. And since the volume is 24, hopefully you can realize that if I ask you the question, would you be able to use the 25 milliliter round bottom flask for this experiment? The answer to that should be no, because this volume will be too close to the total volume that can be handled by that flask. So you will be using a 50 milliliter flask, and so somewhere around halfway is where you would see the mark. Add the boiling chip to it. Consider that as a done deal each time whenever you are heating, because you don't want the heat cells to get developed. Now you have to connect this to a fractionator. Whoa. Now, in order to prepare the fractionator, also let me not have to repeat that each of these parts, each of the joints need to be greased and all of that good stuff. That's, considered by default now. Anytime you're using, you are supposed to do those kind of things. Alright, now how do we prepare the fractionator? The fractionator will be the distilling column, the fat column. There are two columns in your kit, and you're going to be using the distilling column. Realize that it's a tube within a tube type of a system. And so typically you could have a water in and water out of this, but we are not going to employ a water jacket here. There are 3 notches inside, so what I would very strongly recommend is before you get started, it's a good idea to just inspect your distilling column that it's not broken. Otherwise you will spend all this time setting everything up, and if the notches are broken, then there's going to be a problem. So make sure that the notches are intact at the bottom, and then you're going to roll, not dump, not throw, but roll from the side. You should roll a nickel sphere, a nickel bead, to settle all the way in. That nickel bead is big enough that it can hold the glass beads on top. Now, the best way to roll will be to basically make the angle of this condenser, close to about maybe 45 degrees, and then just roll on the side. As you do that, and the nickel bead is sitting, at the bottom, right on top of the 3 notches. Now, using a powder funnel very slowly, and if you don't see a powder funnel, you can absolutely use a weighing boat or paper, or just one at a time, whatever is convenient. But you want to transfer, powder funnel usually works the best. You want to transfer the glass beads that we provide. Go slow because it fills up pretty fast. What you want to do is you want to fill up all the way up to that mark. Alright, now once you have that, so here I'm going to say that this is your fractionator. And like I said, we are filling it up with the glass beads because we want to increase the surface area and provide the time for each of those vapors to go through the system. Now, past that, you're going to connect that with a still head, which will be connected to a thermometer adapter. And the thermometer is going to measure the temperature of the vapors as they are going to go through. You don't want the thermometer all the way in, because if you do that, then it's not going to measure the temperature of the vapors, and actually the problem would be that the hot vapors, when they see a cold surface, they're going to start going back down this way rather than making it through the condenser. So it should be right at that Y junction. Now, the thinner condenser is what you're going to put next. So water in, water out, H2O out. Again, that 2 is a tube within the tube, and since you have the water jacket, water supply, start the water supply prior to your heating, because you don't want to lose any vapors. And this will then be connected to the receiver adapter, and that is being dropped into a measuring cylinder. A 25 milliliter measuring cylinder is just fine, because you will be collecting overall approximately around 16 to 18. That's my target usually. Most people on an average are able to get to about 16 to 17 milliliters. If you're able to cross 18, that's good, but never more than 20. You never want your round bottom flask to completely get dried up. Okay, so that's where you're going to collect. Now, if you feel that the round bottom flask is kind of, way too, or rather the graduated cylinder, not the round bottom, but the graduated cylinder, if that's way down, then you can absolutely use one or two of those cork rings to hold that. So you can use two ring stands to, of course, hold the round bottom flask and the receiver adapter here as well. This, by the way, is being heated with a heating mantle, not water bath, but a heating mantle. And you should begin, when you begin, you should begin slightly slow. You don't want to heat it at a very high speed. If you heat the heating mantle too quickly, then essentially all of the reaction mixture, the temperature will spike. All of the reaction mixture would want to go through the fractionator, and so you would not be able to separate the components out very well. The rate should be that as the liquid begins to collect, you should be able to actually count. It should not seem like Niagara Falls or even like a running, a faucet. You should be able to go one drop every 2 to 3 seconds. So Mississippi, 1 drop, Mississippi, 2 drop, Mississippi. So you should be able to count every single drop that is getting collected in your round bottom, I keep calling it round bottom flask, in your graduated cylinder over here. Okay, now let's take a look what I want you to record, because that's another important thing to worry about. So all right, so realize that as you begin heating, the first fragment that you expect to collect should be consistent, should contain mainly dichloromethane, because that's the least boiling of all. So what I want you to do is create a table in your observation, in your notebook, which will have volume of distillate collected, and it will have a temperature. Your thermometers can read up to the first decimal place, so it's a good idea, even if it's a 0, you should record 20.0, 30.0, 30.5, so I'll go up to the first decimal place. Now, when nothing has been collected, so 0.0 milliliters, you should record what the temperature is. So that's your beginning temperature. And then every 2 milliliters, I want you to record what the temperature is. Irrespective of what's going on, I want you to record this every 2 milliliters. So 0, 2, 4, 6, 8, all the way. I want you to go up to 18 is my dream come true. Okay. And if you're able to go somewhere between 16 to 18, that's a good thing. But that's what we are going to hope for. Now, realize how, because you're going to be graphing this out. So realize what your graph is going to look like. That's the next thing that I'm going to talk about at a later time. And if you don't have access to a computer, let me know so I can help you plot that, essentially within the lab, or after you're done with the lab if time permits, or you can go to one of the computer labs and use MS Excel. So you're going to plot, and you're going to plot temperature in degrees Celsius against volume of distillate. Couple things about plotting. Milliliters. So temperature on y-axis and volume of distillate. Now we are going to begin when no volume has been collected. So that's what we are going to begin, 2, 4, 6, so on up till 18. So sometimes, if you are collecting, let's say at 17.5, you should just know that it was 17.5, rather than recording that as, 17 or 18. But you should know how much volume was collected. Let's say the temperature that you began with was maybe 20. And then when 2 milliliters was collected, maybe it remained 20. And then when 4, maybe it increased to about 24. All right. And then it keeps going, and then it becomes constant. So whatever it looks like, that's what you're going to record. Realize the concept here. It's a mixture of 3 different kind of liquids. So the kind of forces of interaction that are built between the molecules of, let's say, dichloromethane with cyclohexane, or cyclohexane with paraxylene, and paraxylene with dichloromethane, that is going to essentially dictate the kind of energy that will be required to break and go through your vapor, go through into the vapor phase. So it's not necessary that, even though theoretically we know that for a pure sample, it's not necessary that you're going to see temperatures kind of exactly where we are expecting them to be. It's possible that the temperatures will be a little bit low, because it all depends on the mole fraction. But you're just recording that temperature as long as you have made sure that your thermometer is at that Y junction that I was talking about, the Y junction of the still head. Now, also realize, once there is a liquid that is being boiled and is being collected, all the energy that you provide, that is being used to break those bonds and go through that transition. And then once that fragment has been collected, the temperature will change and there'll be a steep increase. So technically, irrespective of the temperature, but your graph should look, kind of like this type of a section where first temperature dichloromethane goes away, second temperature cyclohexane, third temperature paraxylene. That's what we are looking for. It may or may not look exactly like that, but that's what we are hoping for. You have to get essentially the best fit curve for the steep part and the horizontal part separately. So it should look like this ladder like system. Now, what I want you to do is collect up to 18 milliliters. So hopefully you can see that we had used 8 milliliters of dichloromethane, right? We had used 16, or rather 8 milliliters of cyclohexane, and then 8 milliliters of paraxylene. So paraxylene is going to be my last fragment. And since I'm going to stop heating around 18, that should tell you that you would have removed the dichloromethane and the cyclohexane from your system. And what remains should technically be pure paraxylene. So how will you figure out that it is in fact pure paraxylene? You're going to do two things. You're going to take the refractive index, and you're going to do B, take the IR of that. So if the IR gives you a purer value, in the overtone region, for example, in the 1700 to the 2000 region, you should be able to mark that, yes, you do now have absence of dichloromethane and absence of cyclohexane, and you can claim that to be as a data point. The eta, refractive index, is going to be based on the fact that it is essentially a reference, it's a ratio of how the light travels through the medium, which in this case is the compound. So the value that you have for the refractive index, it does not have any units, but it's a very specific value, and you can determine how well the reaction went on the basis of eta. So in this case, this is what we'll do. After you have collected your 18 milliliters, you're going to go look for what's remaining in the flask, not what went up to in your measuring cylinder. That's not what we are interested in, but rather what remains. You probably should have somewhere between 4 to 6 milliliters of pure paraxylene, or as pure as possible. Now, if your lab doesn't go as well, there's a possibility that you may not be able to push it all the way to 16 milliliters, and maybe in terms of time, I will make an announcement, okay, everybody, stop heating, and so you'll have to pay attention to those kind of things. And it's a possibility that you may only be able to go up to 10 milliliters or 12 milliliters. Well, your eta would be reflective of that. Okay, so what you will do is you will come to the refractometer and you will measure eta, and then in your lab manual on page 76 there is figure 5.1. What I want you to do is I want you to take a picture or take a scan of that and really enlarge it. Okay, so print it over the entire page. This is what it'll look like. Look. On the y-axis you have mole percent of paraxylene. On the x-axis you have eta. Alright, so I will give you the eta value for the mixture, and suppose this is what it looks like. So suppose my value comes out to be 1.44. Okay, 1.44. Don't you think that you can extrapolate on the curve and you can read from the x-axis as to what your mole percent was for the starting mixture? And if you can do that for one, you can do that for any solution for that matter. So what I want you to do is determine eta, and measure essentially the mole fraction. Of course, a dream come true would be that it should be as pure as possible, but whatever you get is what we are going to go with. Now, that will be one of the data points that you will present, and that will give you an idea of how pure or impure your sample is. So you're going to give me eta, you're going to give me IR, you're going to give me the volume that you collected overall, and that's what we are going to discuss now. Talking about eta, how do we actually run that? Just to kind of give you a flavor, a refractometer works very similar to, so it looks very similar to a microscope. When you look through the window, when you look through the eyepiece, this is what you're supposed to see. On the bottom window, you will see a scale. That's what you're going to read. On the top window, you're going to see a cross section, like a crosshair, and you will see a region of darkness and a region of brightness. And your aim is that you put the entire darkness section to be at a very sharp interface with the bright section. That's what you're aiming for. And it should also essentially pass through the midpoint of that cross section that you see. That's what you're aiming for. So if you see kind of like a, fuzzy blue or red type of a color, you need to redo that again. Now, as you do that, you will see that the cursor is going to change. So there is a coarse reading, there is a fine reading. The coarse reading button is on knob rather is on the left hand side of the refractometer. The fine reading is on the right hand side. There is a top scale. Okay, so the top scale would read, let's say, 1.4. And I'm just coming up with some random numbers. And suppose this is 1.50. And it starts 1, 2, 3. And it is at 1.43. Okay, so you know that the 1.43 are the first two decimal digits, and then there's a vernier scale between 0 to 9 that it cuts at. So that will give you the third decimal digit, and then the fourth and the fifth are going to be obtained by the vernier scale itself. So you will look at the reading as a combination of the two scales, and that will give you information on what that number is going to be. And you must report 5 decimal places to meet the lab to meet the lab expectation for the ADA. And you're going to read that ADA on your curve, extrapolate that on your curve to read essentially the mole fraction. The mole fraction is what you're going to report in your conclusion. So what is it that you will have in your conclusion? Let's take a look. Your conclusion will discuss the IR, the changes in IR essentially, the ADA. It will discuss the volume that you collected. It will discuss the observation table that you had, and the graph that you plotted. Of course, you will be including the eta graph to determine the mole fraction. And again, don't let that be considered as if, okay, yeah, she'll figure it out. You're supposed to give me what that mole fraction is. So write that as a statement. And that is pretty much the lab.